Hello everyone. First section that we're going to go over using our new online format, section 3.4, the chain rule. The chain rule generally deals with composition of functions. So a little refresher on composition of functions. If we have function f of x, let's say that is an x squared, and function g of x, we'll make that one e to the 3x. Composition of function, you're basically substituting one function into another. Two different common notations for that. The circle notation f of g of x, which also can be written with the more sort of user-friendly parentheses f of g of x. So in this order, it's saying keep the framework of function f, which is saying f is something squared, and then plug in function g of x, in this case e to the 3x. So f of g of x for this one would be e to the 6x. Power to power, remember you multiply. And also just a quick little reminder, composition is not a commutative operation. If we look for g of f of x, given the same two functions previously mentioned, now it's saying keep the framework of function g, substitute in function f. So function g has the framework of e to the 3 times something. Our something is function f, which is the x squared. So g of f of x would be e to the 3x squared, not equal to e to the 6x. So the order is important in composition. So now that we have the idea of composition sort of refreshed, we want to look at sort of a special case of the chain rule, which is the general power rule. And we will sort of derive that. This is not going to meet the standards of a mathematical proof, but it will give us some idea of the thinking and where the rule comes from. So the first power we'll start with is letting f of x be g of x quantity squared. These are no longer references to the previous two functions. These are just two arbitrary functions, f of x and g of x. And we're going to assume that they're both differentiable on some open interval. Well, the fact that we are squaring g of x means I basically have g of x times g of x, just definition of square. Now we did learn the power rule before the break and all this excitement of late. So f prime of x, listening to the power rule, we differentiate the first factor, so g prime of x, times, and then we keep the second factor, g of x, plus, and then the factors trade roles. So now I'm going to just hang on to that first factor and multiply it by the derivative of the second factor. So notice g of x times g prime of x, multiplication of functions, is commutative as opposed to composition, which is not. Each one of these is a g prime of x times a g of x, and we have two of those. We're going to hang on to that result. If we let f of x equal now some arbitrary differentiable function, g of x again, this time cubed, well, we can say that that is g of x quantity squared times g of x. And we can apply that power rule one more time. So f prime of x is equal to derivative of the first factor. Our first factor is g prime of x. We use the previous result. So that would be 2 g of x, g prime of x, times, keep the second factor, g of x again, plus, now they trade roles. Now I have to just hold on to this g of x quantity squared and multiply by the derivative of the second factor, which is g prime of x. So a little bit of cleanup on that. F prime of x is now 2 g of x squared g prime of x plus g of x quantity squared times g prime of x. And notice those are like terms, so we can shorten that guy down. So now we can say f prime of x is 3 g of x quantity squared times g prime of x. Again, we're going to sort of keep that result handy for just a minute. And we'll look at a fourth power and then look for a pattern. So now we're going to let f of x equal g of x quantity raised to the fourth power. I'm going to hold off on differentiating for a moment and just put it into a more convenient format. So we'll make that g of x quantity cubed times g of x. That way we can apply the power rule and go back to our work at the bottom of the previous page. So f prime of x, applying the power rule, derivative of g of x quantity cubed, our last result, we saw that that was 3 times g of x quantity squared times g prime of x. So that's the derivative of our first factor times, hang on to that second factor, plus, since we're using the power rule, now they trade roles. Now I hang on to the first factor and multiply it by the derivative of the second factor. The derivative of our second factor in this case is just whatever g prime of x is. Okay, now notice I have a g of x quantity squared times a g of x here, so a little bit of cleanup. And f prime of x is now 3. That's a messy 3 there. That'll do. 3 times g of x quantity cubed times g prime of x plus g of x quantity cubed times g prime of x. Like terms again. So we'll put them together. So f prime of x is now 4 times g of x quantity cubed times g prime of x. So summarizing what we saw so far, when f of x was g of x quantity squared, our derivative f prime of x ended up as 2 times g of x times g prime of x. When f of x was g of x quantity cubed, we saw that our derivative f prime of x was 3 times g of x quantity squared times g prime of x. And our last one that we just finished, f of x, originally was at the top of our page here, g of x quantity raised to the fourth, and we ended up with f prime of x being 4 times g of x quantity cubed times g prime of x. So you may notice the pattern here, and this is why we call it the general power rule, because it looks just like that power rule that we learned early on in differentiating polynomials. The exponent becomes your coefficient. Sorry, I have an 8-month-old at home. You can maybe hear her in the background there. Mom's tending to her right now. My apologies, my exponent becomes my coefficient. G of x stayed each time and just had 1 subtracted from the previous exponent. And then we always, this is the most commonly forgotten part, don't forget this guy, multiply by whatever g prime of x is. So in general, f of x equals g of x quantity raised to the n power would imply that then f prime of x is going to be n times g of x to the n minus 1 power, always times g prime of x. So where does this come in handy? Well, if we have a function like, say, f of x is 7x minus 8 to the 15th. I could multiply out 15 of those binomials or make a very large Pascal's triangle for my coefficients. The numbers would get pretty out of hand pretty quickly though. But with our general power rule, we can differentiate this without too much sweat. So f prime of x, using our general power rule, exponent becomes a factor. Hang on to our 7x minus 8. That's what's acting as our g of x at the moment. Instead of 15th power, now we're down to the 14th power. And don't forget this last part. Do it in red if you need to. Highlight it. Do whatever you need. Most often forgotten part, multiply by the derivative of the 7x minus 8. That is a linear, so its derivative is just the coefficient of the x, in this case the 7. And then we're just doing a little bit of cleanup work to finish it off. So f prime of x, 105, by 7x minus 8 quantity raised to the 14th power. The g prime of x isn't always necessarily a constant. You'll see that in the next example. If we have g of x is, let's say, x to the 4th plus 2 quantity raised to the 5th power. Yes, we could expand that and factor the result. Again, a little bit more work than is necessary. If we just follow this general power rule, g prime of x, exponent becomes a coefficient. Hang on to the x to the 4th plus 2, drop the exponent by 1, and don't forget to multiply by the derivative of, in this case, the x to the 4th plus 2. That is just a regular power rule of 4x to the 3rd. And then we clean up where we can. So g prime of x, 20x to the 3rd times x to the 4th plus 2 quantity raised to the 4th power. And let me just make sure I'm self-centered in here. Okay, looking good still. One more example, then I'm going to have you all pause the video and try one. We'll try p of x is the reciprocal of the quantity x squared plus 2x minus 5, quantity raised to the 4th. So this one I do have one little bit of business before we differentiate. So p of x is x squared plus 2x minus 5, quantity raised to the negative 4th. So p prime of x, negative 4 times x squared plus 2x minus 5. Subtract 1 from the exponent, careful here with your signs, and multiply by the derivative of the argument. In this case, our derivative of the argument is actually going to be two terms, so times 2x plus 2. So p prime of x is negative 4 by 2x plus 2 all over x squared plus 2x minus 5, quantity raised to the 5th power. If you want to either distribute the negative 4 or factor the 2 and make it a negative 8 outside, either of those forms are acceptable. This form is also acceptable. So there's, just as a heads up when you're doing the homework, sort of 3 common ways that the author could leave the answer. One's not necessarily better than the other. So any of those would look just fine. So here's another nice application of the general power rule. I'll put the problem up and I'll recommend that you just copy the problem down, pause the video, try it yourself, then play it to see if what you thought should happen matches with what happens with it. So we'll look at r of x is cube root of the quantity x squared plus x minus 11. So I'd pause it here and give the problem a try. Welcome back. So this one, we did have one step. We're still at r of x. Notice we're not at r prime of x just yet. Since I'm just changing the look, I haven't taken any derivatives. This would be x squared plus x minus 11, quantity raised to the 1/3 power. If this were at the bottom of a fraction, that would make it a negative 1/3 power. But here, simply a 1/3 power. So similar to the previous example, sometimes you will have to do a little bit of legwork at the start of the problem before applying the general power rule. So then we just apply the general power rule. R prime of x is then 1/3 by x squared plus x minus 11. Take 1 off of the exponent. And don't forget to then multiply by the derivative of your argument, your function that we were treating as the g of x. So in this case, that would be a 2x plus 1. And then just a little bit of cleanup. So r prime of x looks like we just have the 2x plus 1 upstairs, and then 3 by the cube root of x squared plus x minus 11, quantity squared. Again, just as a quick little heads up, we may see it with the exponent notation as well. 2x plus 1 all over 3 by x squared plus x minus 11, quantity raised to the 2/3 power. It's an ugly little 3 down there, but that's a 3. Okay. So that's our friend, the general power rule. Now we build up to the chain rule. Some people even refer to it as the composite rule. We'll begin with one of our famous let lines. So we'll let m of x equal f of g of x. So remember, this is equivalent to, if you're comfortable with this other notation. So if I want the derivative of m of x, m prime of x, I can use the limit definition here. Limit as h goes to 0 of f of g of x plus h minus f of g of x all over h. So as written, there's not much that we can do with this, but with a little bit of work with this, we're going to multiply by something worth 1, and that's really going to help us out. So I'm going to multiply top and bottom by g of x plus h minus g of x. So as long as I've multiplied top and bottom by the same non-zero quantity, I've changed the look but not the value. So next I'm going to go ahead and trade these denominators out. So this is basically, if you're thinking of a quick little side problem, 2/7 times 3/5, you will still get the same answer as 2/5 times 3/7. That's the idea I'm going to use here. I'm going to leave my numerators alone, but I'm going to flip my denominators, and since it's multiplication, we are allowed to do that. So m prime of x is the limit as h goes to 0. So I'll hang on to that first numerator, f of g of x plus h minus f of g of x over, now I'll flip my denominators, g of x plus h minus g of x times, we'll hang into that first numerator, second numerator, g of x plus h minus g of x, and we've got an h downstairs there. So this one we would recognize as being f prime of g of x. This one is the limit, we take the limit as h goes to 0. This is g prime of x. So I'm going to go ahead and that down. So our chain rule then says that m prime of x, f prime of g of x times g prime of x. Now there is another way that we can look at this rule. We can think of it in terms of u substitution as well. Some people do find that easier as well. If temporarily let y equal our f of g of x, and we let g of x be temporarily replaced with a u, then y is some function of temporarily of the variable u. And if I want dy dx, I can find two things. Right now, y is temporarily a function of variable u, so I can find the derivative of y with respect to the variable u and multiply by the substitution we did. So differentiate this u equation, treating x as the variable, and notice the du's would cancel and give us dy over dx. Alright, so let's do a couple of those. Let's let y equal u to the 1/2, and let u equal 5x squared plus 2. If I want to find dy dx, first I'll find dy du. 1/2 u to the negative 1/2. And I'll also need du dx. In this case 10x. So dy dx is the product of those two. So 1/2 u to the negative 1/2 times 10x. So dy dx. So 1/2 of the 10 is 5. So we have 5x over u to the 1/2. So I went ahead and took care of that negative exponent. Now, notice these are written in terms of y's and x's. I have an extra variable there. I have a u in there. We just use back substitution to get it back out of there. So u was the same as 5x squared plus 2. So our derivative of y with respect to the variable x, 5x upstairs, downstairs, square root or raise it to the half power, 5x squared plus 2. Can't touch these 5's. This one is just raised to the first. This one is part of an argument. So that's as far as we can simplify that guy. So this was another one that we could have really done just the general power rule. This next one, we couldn't use the general power rule. If we have, well, let's say we'll make it an f of x. F of x is, well, let's say e to the 9x cubed. This is not something I can turn into a general power rule. And we did learn before how to deal with e to the c times x, but not c times x to a power. Well, here I just have to pick my y and my u. So we're going to let u equal this entire exponent, the 9x cubed, which would make our y, we'll temporarily replace f of x with a y, e to the u. And then I have to just differentiate each one of these pieces. So derivative of u with respect to variable x is 27x squared. Derivative of function y with respect to the variable u, derivative of e to the u is still just e to the u. Run out of real estate there. Let's see. Just continue him over here. So then dy dx is the product of those two, 27x squared times e to the u, and put your original variable of x back in it. So dy dx, 27x squared e to the u, remember we said was the same as a 9x cubed. Okay. All right, so now I'm going to put a couple of U-try problems up. I'll put, actually there's 3 of them there. Once you've copied them down, go ahead and pause it and see what you come up with before watching what I do. So first problem, we'll do y equals u to the negative 5th, and u is equal to 2x cubed plus 4. Second problem, we'll do y is e to the u, and u is, let's do 3x to the 4th plus 9. And third one, y is natural log of u, and u will be 2x minus 7. Okay, so go ahead and pause, and for each one of those, see if you can find dy dx. Okay, welcome back. So for the first one, I'll find dy du. So that would be negative 5u to the, careful with your signs, negative 6. And du dx, 6x squared. So dy dx is just the product of those, so negative 30 u to the negative 6 x squared, and just take care of your negative exponent and get your original variable back in. So negative 30x squared over u to the 6, so dy dx. Negative 30x squared is still up top, and our u is the same as 2x cubed plus 4. So 2x cubed plus 4, quantity raised to the 6 in the denominator. Our second one, dy du. Hopefully you remember that from the previous example. That's just e to the u. Du dx. For this one would be 12x cubed. So dy dx, the product of those, so 12x cubed e to the u. So dy dx by substitution is 12x cubed e to the u this time was the same as 3x to the 4th plus 9. And our third one, dy du, derivative of natural log of u is 1 over u. Hopefully you remember that from our exponents and natural logarithms section. Du dx for our third one would be a 2. So dy dx, product of the two of those, so 2 over u. So dy dx is 2 over u is the same as 2x minus 7. Okay, so sometimes we do multiple substitutions in one problem, but the idea still holds the same. So on this one, we'll take a look at y equals e to the 10 plus natural log of x quantity squared. So note here, not natural log of x squared, which would turn into